Okay, well, welcome to 4youelectricals. Today we'll discuss about the DC missions basics. Okay, how? So, what basic requirement to generate the EMF? So, this is first we have to know about what is the basic uh, needs for the generating EMF. So, we need the first one conductor, magnetic field, and relative speed. From this one, so we'll get the here from this one for the conductor, magnetic field, and relative speed. So these are three things we need for to generate the EMF. So any either AC or DC. So the three things are needed for to generate the EMF. Next, how EMF is induced. Okay, so whenever a conductor cuts the magnetic field, an EMF is induced in it. So this is the Faraday's first law of electromagnetic induction. So EMF is generated when a conductor cuts the magnetic field and EMF is induced in it. When a conductor cuts magnetic field and EMF induced in is the states of Faraday's law of first law. Okay, Faraday's first law of electromagnetic induction. Next, what are the types of induced EMF? So here they have the two types of induced EMF. First one dynamical induced EMF. Next one self-induced EMF. Next one. So here the word dynamic. Okay, the meaning of the word dynamic is so dynamic means it's related to the motion. Okay, is related to the motion. So this word clearly related to the motion. Next, so dynamically we know the next big thing is dynamical induced EMF. So EMF is induced when the flux linkages with the changes. The dynamic induced means EMF induced when the flux linking in a conductor changes. Okay, EMF is induced when the flux linking a conductor changes. Okay, here flux is changing. Okay, so here we're generating the flux is flowing from first north pole to south pole. Okay, here the conductor is rotating. The conductor is rotating. Here due to the rotation of this conductor in this way, the flux cutted by the conductor and EMF is induced in here. Okay, the direction is changed. Okay, so this here in this way we can use that. Okay, this way dynamically induced EMF is generated. Next, any dynamically induced EMF is conductor moves in a stationary magnetic field. In the dynamically induced EMF and EMF, the conductor moves in a stationary magnetic field. So this is a stationary magnetic field, north pole, south pole. Here's the stationary magnetic field. So it will be generated. Next, an EMF is induced in the conductor when it's motion. Okay, here EMF is induced when the conductor is in a motion. So with the stationary conductor there is no EMF production. So we need to generate the, so whenever it is having the motion only EMF is induced. Without having the motion it cannot generate the EMF. Okay, now here dynamically induced EMF, how it is been. So here north pole is there and south pole. Here we're placing the one conductor, but the stationary position is there. There is no EMF production. Okay, so the current, the flux is flowing through north pole to south pole. Here conductor is placed here V. Next, so whenever the conductor is in motion, so when the conductor is in a motion with the velocity v, so we'll get the PLV sine theta. Okay, from north pole to south pole flux is changed. Okay, from north pole to south pole flux is flowing. So conductor is rotating conductor in this way. Here v sine theta, v cos theta will get that. Okay, here the rotation directional speed. Okay, we'll get the values BLV sin theta. Poles, conductor and field. Okay, so how were they going derivation for the dynamic induced EMF? Okay, here magnetic flux density is B, Weber per meter square, Weber per meter square. Next, the conductor is moving with the velocity V. Okay, with the velocity V, meter per second. The conductor length is the meters. If the conductor moves through a small distance dx, in the time at dt seconds. Okay, the area swept by the conductor is length into dx. Okay, the small distance length into dx. So flux cut by the conductor here, flux in this way, flux cut by the conductor is BL dx. So according to Faraday's law, EMF induced in a conductor is given by N d phi by dt. So that is equal to N B into L into dx by dt. That is equal to BL dx by dt. When if considering the number of conductors is 1, so that is the BLV volts. Next, if the conductor moves at an angle, okay, conductor moves at an angle in this way. Okay, conductor moves at an angle theta. For the EMF induced is BLV sin theta, BLV sin theta. So we go for the next, Fleming's right hand rule. Here Fleming's right hand rule statement, stretch out the four fingers. Here stretch out the forefinger, thumb finger and middle finger. Okay, stretch out the forefinger, middle finger, thumb finger of right hand, so they are right angles to each other one, each right angles to one other. Okay, if the four fingers of the direction, okay, the four fingers of the direction points in the direction, the magnetic field will flow, the magnetic field will flow. And the thumb finger, okay, here the thumb finger indicates the motion of the conductor, motion of the conductor. Then the middle finger, okay, this middle finger give the direction of induced EMF. Next, here, so we can see that here magnetic field, conductor motion, next induced EMF. Okay, this is the Fleming's right hand rule for the generators. Okay, thumb point motion, F means field, middle finger induced EMF. Okay, so how to remember the which one is there? Here thumb, it means for T you have the motion. Okay, for forefinger it will be F means field, for middle that here I, it is the EMF. Okay, I means induced EMF. In this way how to remember the Fleming's right hand rule. Okay, here we have to application of Fleming's right hand rule for the generator. Okay, here whenever stationary magnetic field and rotating conductor, that is AB, so whenever magnetic field is there, okay, the conductor is in rotational way, then if you go want to find out the directions, here F indicates, okay, F indicates the direction of the flux. Okay, F indicates the direction of the flux. Next, thumb finger indicates the motion of the conductor. Next, this is the induced EMF. Okay, middle finger indicates the induced EMF in the conductor. Okay, this is the Fleming's right hand rule and dynamically induced EMF derivation. Okay, this application go here. So here AB is moving upward. Okay, AB is moving upward direction. Right hangs to uniform. Okay, the magnetic field hangs to uniform. Next, by Fleming's right hand rule, the direction of induced EMF from that is B to A. B to A. Next, if the motion of the conductor is downwards, okay, if the motion of the conductor is downwards, the direction of induced in will be A to B. A to B here. Okay, so this is the application of the Fleming's right hand rule and dynamically induced EMF. Okay, thank you. This is for electrical. If you did not subscribe us, put the subscribe button, and if you like it, put the like button and share it. Thank you. This is for electrical signing off.